Hey everyone, and welcome to today's live stream, SLAM-Boree. My name is Andrew Jenko, and I'm a Senior Customer Success Engineer with Robotic. For our existing customers, if you have had questions or support needs in the past, we have likely spoken or communicated via email. We are really excited to have you join us as we dive into a crucial technology for modern data collection, SLAM, or Simultaneous Localization and Mapping. SLAM is a game-changing technique that allows us to accurately map environments, even in areas where traditional GNSS-based methods struggle. Whether you're working indoors, in dense vegetation, or in restricted airspace, SLAM offers a flexible and efficient solution for LiDAR-based mapping. Please note that during the live stream, if you have any questions, please ask via chat, and members of the ROC team will do their best to answer your questions as quickly as possible. If necessary, we will discuss certain questions and answers in the live stream. Additionally, before we kick things off, I would like to take a moment to thank you again for attending. Your attendance and participation is greatly appreciated and is a major factor in how ROC is able to improve our offerings over time. With all that said, let's get into it. So what exactly is SLAM? Simultaneous Localization and Mapping is a technique that allows a device to build a map of its surroundings while simultaneously determining its own position within that space. This is incredibly useful in environments where GNSS signals are either weak or completely unavailable. Think about places like indoor facilities, warehouses, tunnels, or areas with heavy vegetation where satellite signal may be obstructed. Also, locations with airspace restrictions where flying with a drone simply is not an option. By using SLAM-based LiDAR, we can still achieve high accuracy mapping without relying on satellite positioning. All right, so now let's talk about why SLAM is such a great fit for LiDAR workflows. Our goal in LiDAR mapping is to collect precise, high-quality spatial data, and in many cases, drone-based LiDAR is the go-to method. But in environments where drone operations aren't feasible, whether it's due to, as I mentioned, regulations, safety concerns, or physical obstructions, SLAM provides a way to gather that same level of detail from the ground. A perfect example of this is a dataset we previously collected at Union Station. We looked at this in our previous live stream. This is an active train station with complex structures, covered walkways, overpasses, and vertical facades that would be very difficult to fully capture with a drone. Not only are there physical obstructions, but in an active public space, flying isn't exactly recommended or legally allowed. With SLAM, we were able to capture the entire site safely and efficiently from the ground, ensuring complete coverage of key structural elements. And it's not just for train stations. SLAM works exceptionally well in completely GNSS-denied spaces like buildings, tunnels, and underground environments. If you're mapping an indoor facility, you still need accurate calculations for floor plans, surface areas, height measurements, and structural integrity assessments. Since drones can't fly steadily inside a building, SLAM-based LiDAR is the best solution for precise, handheld, and mobile data collection in these environments. So with that, we're going to compare SLAM to traditional survey methods. In a conventional survey workflow, you might use a total station, which would require multiple setup points, take a crew of multiple people to operate, and be time intensive. Not to mention total stations, the equipment itself is expensive and require careful placement to ensure accuracy. With a ROC SLAM system, specifically using our R3 Pro V2 or R3 V2, you can accomplish the same data collection with a single operator. Instead of setting up a static system, you can walk the site freely, capturing real-time data. This not only speeds up the process, but also allows for better coverage. With SLAM, you can perform detailed painting methods to capture underpasses and complex structures. You can also collect data in tight spaces that traditional methods struggle to reach. get a good job, and you can get the job done safer, quicker, and more efficiently. So one thing I do want to mention as we kind of get into this, with SLAM, it's a great technology, and as we mentioned, it's going to be really applicable in some areas where the a drone-based method is not going to be appropriate. But please understand that it's not a direct one-to-one substitute for drone-based surveying. Your drone-based surveying is going to have its own unique workflow, limitations. You're going to take certain things into account when setting up your data collection plan for that area. And you're going to do that with similarly for your SLAM data set. So I know when I started out, my approach to SLAM was along the lines of, all right, we can just put the unit on the SLAM dock, walk around and collect data, and that's going to be great. And I learned really quickly that's not the case. It took a great amount of time of working with colleagues here at Robotic to really understand the best workflows and the reason behind them. And that was a bit of a mindset change that I had to adjust to. Was SLAM is not a direct substitution for drone-based surveying. It's something that's got its own set of limitations, its own set of collection parameters to keep in mind. And for each site that I go to where I'm collecting SLAM data, I'm always taking the time to think about how I want to approach my data collection for that site. So my objectives and goals for that data set will be met. So with that little aside, to sum it all up, SLAM technology is revolutionizing LiDAR data collection, making it more accessible, efficient, and adaptable to challenging environments. Whether you're working indoors, on a complex site, or in an area where drones just aren't an option, SLAM ensures that you can still achieve high accuracy mapping. Now that we've covered the basics, let's dive into a real-world demonstration of how SLAM works in action. So we're going to start with our Rock SLAM offerings, because we've gone over the fundamentals of SLAM and its advantages in LiDAR mapping. So we want to talk about those specific options that Rock SLAM offers and how you can leverage them for your projects. As I mentioned earlier, we have two primary devices for collecting SLAM data, the R3 Pro V2 and the R3 V2. Both of these systems provide high accuracy SLAM-based LiDAR mapping, but your workflow can be customized based upon your specific needs. Also, we want to talk about some other key parts of the Rock ecosystem, and that's going to be your SLAM dock. Right now, we have two offerings. There's the V1 SLAM dock, and this is just going to be set up so you can capture SLAM LiDAR data only. We also have a V2 SLAM dock. That's our more recent offering. This will, again, capture your SLAM LiDAR data, but it's also going to allow for video collection to be able to use to colorize your point cloud, as well as GNSS data collection, if applicable, and your site allows it. So those are some of the hardware offerings. So this means that if you want to integrate additional data layers, such as colorized point clouds or georeferencing your SLAM data, you'll want to use that V2 SLAM dock with your R3 Pro or R3 V2 system. Now, once you've gone ahead and collected your SLAM data, Rock offers 4 primary ways to process it within the Rock ecosystem. And you can see that in the slide right in front of you. Let's break them down. So the first is going to be what I would say general SLAM or SLAM-only processing in Rock Desktop. This is going to be the most basic workflow, and your SLAM data is processed entirely in Rock Desktop without any additional data layers. This would be something that would, again, you would be using the original SLAM dock, or you're not using your input from GNSS or the camera. And so what's going to happen is you would upload that SLAM data into Rock Desktop. You're going to be able to process it. You can adjust your trajectory, so the coverage of your SLAM data capture, the distance away from the sensor. And again, not going to be able to colorize it. You'll still be able to see things like elevations, intensity, GPS time, so on and so forth. However, it is going to only have relative accuracy. And later on, we're going to get into the differences between relative versus absolute accuracy. So for this case, though, you're going to be able to, using that data, make measurements, whether they be polygons, point, lines, height measurements, so on and so forth. But it'll all have that relative accuracy. It's also worth noting for that SLAM processing, it's going to be exported in a CRS known as SLAM meters. So that's kind of our SLAM CRS specific. We do offer both meters and feet for that. And then once you've done all your processing in Rock Desktop, you have the same Rock ecosystem workflow of uploading your data set to Rock Cloud, which is going to include that point cloud in a .laz format and your trajectory file. Now, the next option we have is going to be SLAM plus your Insta360 camera. And so that is going to give you a colorized SLAM LiDAR data set. Again, you're processing within the Rock Desktop ecosystem. And this time what you're doing is you're combining that SLAM LiDAR data with your Insta360 camera footage. That will allow you to colorize your point cloud, so you're able to see it in an RGB view. It's also going to allow you to generate photospheres for the Rock Inspect functionality within Rock Cloud. But again, because we do not have GNSS data, that again will be having relative accuracy. So, it'll be exported in SLAM meters or SLAM feet. You have that option. Again, upload it to Rock Cloud, the compressed LAZ file, your photos, and in there you'll be able to inspect everything with not just elevation, intensity, GPS time, but also adding that additional layer of the RGB view. Now we're going to move to the third option. This is going to be your SLAM LiDAR data with your Insta360 camera data, but now you're also including GPS data. So this could be for an area where you are, you're not fully GNSS denied the entire time. So you are able to get GNSS data capture at the start, or potentially, you definitely want it at the start. And so in this, you are going to once again process in Rock Desktop. You're going to be able to colorize your point cloud. But when it is processed, you will have the ability to co-align to that GPS data. This will be a little bit more in line with your standard drone data workflow. So you will need to have a base for our PPK solution when processing. But then what that allows you to do is, depending upon the quality of that GNSS data, when you upload it to Rock Cloud, you can then align it, you can then get it referenced into your CRS of choice, and then complete an alignment to your GCPs in Rock Cloud. So in this case, instead of having relative accuracy, you can have absolute accuracy. Excuse me. And then the fourth option, and this is similar to the third option, but it's going to again be your SLAM LiDAR data. You've got the Insta360 data, so you're getting a colorized point cloud, and you're also incorporating GPS data. But you're incorporating the GPS data of your GCPs, and you're doing that Rock Desktop alignment to your you're completing the alignment to the GCPs within Rock Desktop. And then what that is going to allow you to do is you will have, the first option is align to world. And in that case, you're going to use those GCPs and align everything to your sort of the world in a WGS84 UTM zone CRS. And then you can align to control. So in this case, if you have really poor GNSS data that you collected, you can instead just do this alignment in Rock Desktop, get everything referenced to the world, and then do a further alignment to control. There are some limitations where you do need a higher number of GCPs to complete the control alignment in Rock Desktop, but then what it's going to export is something, again, with that absolute accuracy in a published CRS. So whether you're looking for SLAM processing, just a quick SLAM processing to get relative accuracy and no colorization, or if you need a more advanced and time-consuming workflow where you get colorization and GNSS alignment, the rock ecosystem will provide a solution to match those needs. And now we're going to move on to relative versus absolute accuracy, which we were talking about. So let's talk about this important topic when we're doing SLAM-based LiDAR dataset, relative versus absolute accuracy. And understanding the difference between these two concepts is crucial in determining how precise and geo-referenced your dataset will be. So we're going to start with relative accuracy. Relative accuracy is something that sometimes we might call it internal accuracy. And this means that all the points within your dataset are relatively positioned to each other. So in other words, your point cloud will maintain correct dimensions, structures, and relationships within itself, but it won't necessarily be tied to a global or known coordinate system. And for many applications, relative accuracy may meet your goals. For example, if you're performing volume calculations or monitoring progress, capturing in an indoor environment as well, where absolute positioning isn't critical, SLAM's relative accuracy will provide you with fast and efficient mapping. However, if you need your data set to align to a real-world coordinate system, such as survey grid or a state plane CRS, you'll need absolute accuracy. Absolute accuracy means your data set is correctly aligned to a known coordinate system, giving you a true easting, northing, and elevation values rather than the relative X, Y, and Z coordinates. This level of accuracy is required for survey grade mapping, engineering applications, and precise geospatial analysis. So achieving absolute accuracy is typically going to require ground control points, or GCPs, you might hear me refer to them as, which are surveyed in reference points used to correct and align your data set to real world coordinates. Without GCPs, you're relying solely on SLAM processing, and while you may achieve high relative accuracy, your data could still have some drift when compared to absolute positioning. So with several factors that do influence the accuracy of your SLAM dataset, whether you're working with either relative or absolute positioning, do you want some key considerations to be known that go into data collection? The first is going to be loop closure. So especially if you're not using GNSS data, properly closing your loop is critical to reducing drift in your SLAM dataset. And so drift would be how if you you start to see separation between the same wall or same feature that you've mapped. And basically completing a loop or revisiting known areas helps the SLAM algorithm to correct for that drift. And I do want to kind of highlight that we're talking about something I had to learn. Someone pointed out to me when looking at my data set. We want loop closure, not loop twirls. I would be walking along the survey area and kind of do a small circle that was only about, a 4-foot diameter or something like that. And then someone is like, yeah, that's a loop twirl. That's not loop closure. So loop closure is more, again, that completing your loop and revisiting a known area with a distinct feature. Also, slow and deliberate movements. I found that when collecting SLAM data, it helps to avoid rapid or erratic movements. Walking at a steady, controlled pace is going to ensure smoother data set with fewer inconsistencies. Coverage paths. This is something I also had to learn the hard way. Plan your survey route before you actually collect the data. Typically with SLAM collection in these areas, they can be smaller or shorter than a drone flight. And so with that, you can just take out your SLAM dock and rod without setting up all the equipment and walk your survey area ahead of time. This is going to allow you to ensure that you can achieve full coverage, minimize potential gaps in the data set, and also ensure that you have planned your trajectory so that you are focused on loop closure and returning to those well-defined features on a regular basis to help reduce drift. The amount of time that you can save yourself from a pre-planning walk of 5 to 7 minutes on site can really help save you in a long run. It's also going to help you if you do have underpasses that you need to do the sort of painting motion to get full coverage of. You can really start to think about when you want to do that painting motion relative to the structure of the underpass. Also, you want to think about GNSS and ground control. So if you are requiring absolute accuracy, you need a sufficient number of well-surveyed GCPs spread across your survey area. And so again, with that well-surveyed GCP, something, again, I had to learn the hard way is that if those GCPs are set up a little bit too close to the underpass or a little too close to a structure where you're going to be surveying, you could have reduced satellite connection when you're surveying that point in, higher PDOT values, and you may have less confidence in the XYZ information that you're surveying in for that GCP. And so again, if your goal is survey grade accuracy of 1/10 of a foot, if your GCP, you don't have that survey grade accuracy for your GCP, you're never going to have the confidence that you're getting that in your final data set. So really taking the time to think about where you want to place your GCPs throughout the site, making sure that you can go in and get a good survey of that GCP location to be used in alignment. So as a recap, relative accuracy is going to ensure that everything in the data set is accurate to itself, while absolute accuracy will align your data set to the real world coordinate system. If your goal is survey grade accuracy, proper planning, GCP placement, and best practices for SLAM data collection will be essential. So now we're going to go over some real world examples of our data sets with where we have both relative and absolute accuracy, and how you can go ahead and improve the precision in your workflow. So what's being displayed right now is our first data set. This is the Joyce Street underpass. And this data set is a great example of how you can achieve survey grade accuracy by aligning to GCPs and properly processing the data with co-aligned GPS. So if we were to zoom out, after seeing this underpass, now if you zoom out, we've got great coverage for the surrounding area. And so we started data collection outside of this underpass where we did have good GNSS signal. So we were collecting their GNSS data before we went ahead and entered the underpass. So in this case, we are able to co-align to that GNSS data. So now you can see we are in GPS time, and this will help you understand the path that was walked. So we started on the east side, walked over to the west side, turned around, came back. And what we want to do is anytime we get these data sets, we want to look at the alignment. So we're going to zoom into the walking path that was followed, staying in GPS time. And we can use that to see the repeatability of our data set and how well it aligns. So if we zoom in and really look at it, you can see that we have our blue is going to be that early time, the red and yellow is going to be the later time. There's really good alignment between them. So that's indicating that what we see at the start of data collection is looking the same as what we're seeing at the end of data collection for the same feature. So this is something you should always be doing with your SLAM data sets. Hopefully you have some flat feature and you can come in and really see that alignment between your early and your late time or just overlapping time data set in there. So this gives us an indication that we have a good data set to start off with on that flat surface. So now what we want to do is we're going to take a look at a measurement. And the first measurement we want to look at is going to be our height profile. And it looks like we're still having the, all right. So if we draw a height profile that goes along the underpass, and it passes from the east side to the west side, we can see the finer details. There we go. That's getting drawn in. My apologies. It must not have been saved when I was preparing for it. But when we bring that height profile, this is the real benefit of SLAM. So what you can see is the structure of the underpass support that you're going through. So as we come in there and we go into the elevation view, we're able to see the walking path for the actual underpass. That's nice and flat. But then we're also able to see along the path the structure of those support beams. And again, this is something you're not going to be able to see through drone-based surveying. You obviously can't see through the road, but here you can see that structure. And part of the reason why we're able to get that structure out is because, as I mentioned, we did a painting technique. So in between each of those vertical structures, I was doing this sort of that painting technique. I went from the paved side off into the distance, and then we also went from the non-paved side off to the other, painting to help us get full coverage of the underpass. But this is really highlighting how SLAM can be a great tool for your project. So you're able to get into an area where your drone's not going to be able to fly. You can utilize the fact that you're starting your data set in a GNSS-enabled environment, and then you're moving into that GNSS-denied environment, but you're able to really see the structure of the underpass. You can get measurements off of that. You can potentially see if there are any issues. So that's really helpful. So you also saw that those structures are at a right angle, which is really helpful to see. So that's something that, obviously SLAM is going to really shine in for this location. But now, as I mentioned, we started in a GNSS-enabled environment. We went through that GNSS into a GNSS-denied. And so we were able to do the alignment to the GCPs. We used the workflow in Rock Cloud, very similar to what you would use when aligning your drone data. Now what we want to do is we're going to look at, we're in our intensity view, and we're going to look at our distance measurement 1. And so you can see that we have we have a GCP nearby there. And if we zoom into it, and we might need the measurements turned on first. So as we reload, once those measurements are turned on and we're back into the intensity view to really bring out, that GCP that was set up on site. So now we can see the outline of those GCPs, and you can see that this is after we've done the alignment. And so that GCP has been aligned pretty much right to the center of the target. If you were to make a distance measurement, really splitting hairs, trying to go between where we can interpret the unique point that is the center of the GCP that was measured versus where it is after alignment, you'll be able to see, in this case, the distance measurement, distance 1 that we had, it's less than 3 centimeters. So that's survey grade accuracy. You can see that again right here. We've got multiple distance measurements that show that. So in this case, this Joyce Street underpass, it's a data set that showcases how the strategic feature distribution from the underpass, both the corners when you enter the underpass, as well as the parts, those near vertical support beams. And we've got really good GNSS data before, great GCP. We have 6 total GCPs that were set out for this site, multiple passes over them. We're able to get a survey grade accuracy data set after we complete the alignment in Rock Cloud. And so as you can see, we've got this is all aligned to a WGS84 UTM zone 13 north CRS. So if you were to make a measurement or get an XYZ point from here, it's going to be in that CRS, which is a well-known published CRS. And again, high accuracy. We've gotten it alignment less than that 3 centimeter or 1/10 of a foot. So this Joyce underpass was a really nice example of getting a SLAM data set, co-aligning it to GNSS data, and being able to really see the structures in your area underneath where traditional methods won't allow you to go. So now we're going to move over to our next data set, and this is going to be the Kipling underpass GNSS data. So we collected this in the same manner as the Joyce Street underpass. It's another underpass. If we zoom out, you can tell it's a little bit of a longer underpass, so a little bit longer length. And in this case, as you can see, we have our walking path. So early time, we started, again, with this one, we went west over to the east, paused, came back. You can see the measurements we have there. There were 5 GCPs that were set up. As with everything, we can, do the standard QA. We don't take my word for it, just so we can avoid having to do it. But you would go in, use that GPS time to check repeatability, which we don't have to. So now that we're in the RGB view, what I want everyone to kind of see is that this underpass really lacks features inside of it. Those walls are pretty smooth. You can see that there are some lights off near on the wall, but those aren't very large. And you can see that the roof especially, there's not much going on right there. That is a smooth surface. We actually did multiple passes of this, and I noticed that you can see there's also, we set up some cones inside of it to see if those would be features to help us. But this is, we would call this kind of a feature poor environment. And this data set is going to really help us understand why we want a feature rich environment for getting a data set that can be aligned to within that survey grade accuracy. So what we want to do is we're going to look at the alignment of our GCPs. So we'll turn the measurements on, and we can go over to intensity view. And if we zoom into our GCPs, we can see, and if we were to make a measurement, these are close, but they're not within the 1/10 of a foot or 3 centimeter accuracy that we want. There's a bit of a distance, and we can, we're getting a real-time measurement right now. And these have to be done to the points to get over to the center. We can see with that one, we need to zoom to that distance. So that looks like it's about 7 centimeters. Sorry, I needed to really get in there. So this is going to be closer to 2/10 of a foot. And so we can also see that this GCP is kind of offset towards the underpass. If we were to look at the GCPs on the other side of the underpass, what you'll notice is that they're kind of, again, they're offset towards the, I believe they were offset towards the underpass, or they're just completely off. So what's happening is that because we don't have those unique features that are being scanned and referenced, it kind of puts a limitation on our processing workflow for the when producing the point cloud and then aligning the point cloud. So the other thing in this data set that we have is, you can see, just due to the limitations of where we are surveying, the path leading into and out of the underpass is fairly linear. And so what that does is it keeps all of the GCPs in somewhat of a line. If you remember back to the previous Joyce underpass, there was a bit of a curve in the collection into the pedestrian path after we exited the underpass. And that allowed us to set up the GCPs in a non-linear manner. And so with this, what we really want to see for alignment to GCPs with your SLAM data is that you have at least 3 GCPs that are set up in a non-linear manner. And so in this case, we kind of have just an environment that puts some limitations on how we're able to get final survey grade data, because we have a kind of a not feature rich environment, and we're not able to set up the GCPs in a non-linear manner. That's going to cause us to, as you saw, that 7 centimeter offset as opposed to a 3 centimeter or less. So some people might say, wow, 7 centimeters, 0.2 of a foot, that's great. Realistically, though, for survey grade accuracy, that's too high. I know some people may be looking at this data set and be saying, I see other areas of the path that come off, in this case, down away from our walking path. Why didn't you set GCPs up over there? That was really more due to the fact that once we got up there, we were kind of going into an area, again, without a lot of features for the unit to be scanning during the SLAM collection. It would have gone, it basically was leading us to the road, which didn't have really good defined features. So that was kind of a limitation of our environment. So now, before we move on to the other version of this data set, I want us to look at a measurement we made. It's called height measurement number 2. And so if we click on that, you'll see height measurement number 2. This is right at the entrance to the underpass. And what we see for that height is we have a measurement, or excuse me, we have a height of about 2.567 meters. So we want to keep that height in mind as we move to our next data set. And this data set is just going to be the same version. It's the same data from the Kipling underpass. We just process it without any attempt to co-align to the GNSS data that was collected. So in this case, we might not be achieving our survey grade accuracy. So you'll see in the name, this is relative SLAM Kipling underpass. So we didn't use any of the GNSS data. We just did the SLAM data, and now we're going to look at our height measurement number 1 here, and that's got a height of 2.580 meters. And so in this case, if we remember from our previous data set where we measured that height at it, the difference is only 1.3 centimeters. So this is where coming back to that relative versus absolute accuracy. This is going to be relative accuracy. So everything is, relative internally. But again, the height that we're seeing is the same as when we were using our GNSS enabled processing. So that gives us confidence that we can get repeatable measurements for the height of our features from the same data set, just 2 different processing methods. So that's something I really wanted to show. So even though we're not able to align it to within survey grade accuracy, we can still have confidence in the measurements and the information that we are able to pull out of these data sets. Something to keep in mind as we get rotated about. So everything in this data set is going to be relative accuracy. So what I want you to understand, if you were to actually go to the layers and turn on RGB in this case, or excuse me, turn on elevation, we're already in RGB. You'll see we have an elevation range of, right now it's showing -4 to 4. You can adjust this, but this again goes to that relative accuracy. In this case, this is the Front Range of Colorado. We're well above a mile elevation in feet, or 1,600 meters. And so in this case, everything is just relative. So -4 to 4 or whatever it is. So please keep that in mind when we're looking at some of the information as it comes into this. But that's also, again, a reminder that we have everything in relative accuracy. So now what I want to do is we're going to look at the detailed information that we can get for our site. And so with that, we want to look at, we're looking at the 2 drains on that east side. So if we zoom in, and we're over in RGB, you can see if we zoom in, we have that profile through there. You can see, because we were able to colorize this, these are the drains that exist on the walkways, and using the intensity really helps pull it out. It might be difficult to see, especially right here, because that was actually the north facing side and there's a small curb. And so there's snow that hasn't melted, but you can really see the drain right over there on the right side. And so now, one thing I think for a lot of projects or engineering things, we're always concerned about water. Where is water going? Is it going where we want to go. We are pretty pompous in that regards, that we think we can control water. And so the rock cloud offers you a really great tool where you can see where water will collect. And so this is our water tool. And so you can see we've got a really, that slider just works in there. You can see how it collects. So if we start at a value of -3, or in this case, we'll be at -4, you can see in this case, there would be no water right there. Maybe there's some right down at the base if that went through. But I think what I'd like to do is let's zoom out so we get a nice view of the underpass. That's great. Or let's zoom in and let's get everything set up, and let's change that water view to -3. And so now with -3, you can really see this is, we're getting to the point. If there was water present, this is all going to be, covered. It's going to be draining into those drains, but it'll also be in the underpass. And this allows us to really see how our surface water is going to function depending upon our elevation. So now if we change that -3 to 3.5, because you can also manually change it, we can start to see how, if we increase that, how it starts to affect where the water is going to pool. And we can use that, and we can also go into smaller 0.1 increments to really see how it's going to affect. So at -3.3, and then if we go to 3.2, 3.1, this is starting to really show how, as we change those values at really tight increments, we can see where the water is going on site. And so this is great for your engineering aspects of where's the water going to go when we've got too much of it? Is it going to go to the drains, or do we potentially, does an area need a drain? So now we're at -3.89, and we can see that it's all kind of going towards that drain over on this, that's on the north side. And if we change this to -3.95, we can see basically at this point, we're getting into the area where all of that water is going to be draining into that area, which, one, in this case, it shows that they use some really great design. They got it right. But if someone hadn't, or if you were trying to see where a new drain could be beneficial, this is a really helpful tool. And again, please keep in mind, we're just able to do this with relative accuracy. So we're not using any of the GNSS data that was collected. This is all through SLAM processing, but it really helps us get a great understanding of the site conditions. And I think, we may all think in a lot of cases, SLAM is going to be great for, I always think back to the data set we looked at in the past live stream, Harrison's indoor brewery SLAM, where showing off our Gaussian splats, and how cool is it that there is a Dumb and Dumber van in there, and we can see the pictures on the wall. For a lot of your projects, I imagine the biggest concern isn't where's the Dumb and Dumber van, because there likely isn't a Dumb and Dumber van. It's more, where's the water going to go? Are things draining appropriately? Are there going to be those little bird baths on site? And so this is going to be something in those areas of your project where you can't survey with a drone. You can still, using the SLAM setup, pull that information out of these data sets and have confidence that the design is being met. And again, you can do these really small tweaks to the elevation values to really see how things are going to drain at small intervals. So again, this data set is really showing how using SLAM collection, we can get to kind of the fundamental questions you have about your data site for that, just going in and collecting it. But also you still, as you're showing, you still have RGB, you still have elevation, but you're able to get some really good high quality information out of this data set. So with that, we're going to take a look at another SLAM data set. Again, I hate to think that we're just doing underpasses, but this is, kind of showing the really helpful way that SLAM can be used. These underpasses are areas where, we've done in the past where you've got, areas that are broken up by bridges. You can see here, again, we're using that GPS time slider to really show the collection path. And so that's the midpoint. That's where we turned around. And then we came back over here. We're headed, in this case, your right is going to be the west. So we walked west to east. So this is something that we can focus on. Again, not necessarily the most, kind of eye-catching question you might have to answer. Again, not a Dumb and Dumber van, but this is an underpass that's really close to a school, and what that means is that it needs to be safe for travel, both by pedestrians walking, people on bikes, people coming through with dogs, so on and so forth. And with that, you might have to take into account things like snow removal. And I understand that snow is not going to fall into this underpass because it's got a road. But we do have times where snow stacks up, it gets blown, or even at the edges, you're going to come up there and have to remove the snow. So you do need to understand things like, how are we going to be able to handle just appropriate safety protocols for weather events in an area like this? And so that's how SLAM can be used to really help you optimize these efforts, or think about them and prioritize them for your workflows. In this case, as we see, we have an offset, on the right side, or the left side, which is going to be the north area. That's a straight wall. So if you are coming through with a snowplow, you can't be, obviously, if you're pushing snow into that area, it's going to stack up. If you're coming through and you try and push over to the other side, your right side in here, you have the metal barriers with the small parts. So they only have small openings. It's not going to necessarily allow you to push that through with your plow. So kind of this gets you an idea of how much potential, how are you dealing with the removal up to and through these areas. You can make your measurements that are distance for the distance across of your underpass. You can make measurements for height to make sure that the appropriate equipment can get through. And also, potentially the number of passes that are going to need to be taken into account. So again, for data sets like these, we aren't, what we're interested is getting that full understanding of what the site has as far as, the surfaces, what kind of height we have. You can see there's a bit of an irregular kind of artistic structure that you can see on the top of that underpass. And so it's irregular. How is that affecting it? What can actually get through there? And will it be problematic? So these are all things, again, that your SLAM dataset is really going to help you pull out, which you're not necessarily going to be able to see in a drone-based survey because you're not able to get in there and survey it. So again, also what I want to highlight too is we can also identify, again, those water hazards. So, in this case, well, we have the snow to take into account. We also have when it melts. So if we want to start at 1578.57. And so in this case, we can see how water is going to be present. We do want to see that it is headed over towards that creek side, which is really great. But if we use these increments, if we go from 1578 if we increase this to 0.575, you can also see how this is affecting areas. Yeah, well, now we'll do 158, please. Now we can start to see, using these increments, what's going to happen. So this helps you understand, depending upon surface runoff, rain flow events, and how quickly the moisture is coming down. And if it doesn't have the appropriate time to run off, or where it could be pooling, this again helps you really see that and really figure it out. It's another example, with just understanding your environments in an area where traditional survey methods aren't going to be appropriate. And again, just for reference, the collection time for this site to do a full back and forth pass was roughly 6 minutes. And so from this 6 minutes of data collection, and also, there was some time to go through. As I mentioned, I walked it beforehand, tried to figure out the best painting method. We're really getting these high accuracy, high quality data sets in an area where, certainly you're not going to be able to capture with a drone, and previous methods were very time consuming, very expensive. This was all done, again, just by myself out in the field, less than 10 minutes for data collection. And then we also collected some GCP data. So we're really able to get in there quickly and efficiently to get a great understanding and high quality data of our site. I do apologize that this kind of turned into the underpass and the runoff hour, but I do think that these are a lot of the problems that people are going to be having, or questions people have about, in these types of projects, what are my options for quick and efficient and high accuracy data collection compared to traditional methods, or compared to what I can do with my current LiDAR offerings that are primarily, would be drone based. So, these are those real world applications that I think are really helpful to understand. And again, really highlight the versatility of ROC's offerings, both through our hardware. Remember the R3 Pro V2 and the R3 V2 unit. Those are ones where you are able to attach them to your drone, use our mobile mount, but you can just remove the camera, put it on the SLAM dock, connect it to the Insta360 camera, and you're able to for that one sensor, you've got 3 different types of collection approaches, which that versatility is unmatched. I know we did in our last live stream, that L2 sensor, it's only drone based. So, as we move on, we're going to move on to our conclusion and our Q&A. So as we wrap up the section, I do want to leave you with some key takeaways. As I mentioned earlier, one of the biggest lessons that I had to learn in working with both drone-based LiDAR collection and SLAM LiDAR collection is that those 2 methods are not interchangeable. Each is going to have its own unique workflow, use cases, and best practices. So initially, I thought if I couldn't fly a drone, whether it was due to poor GNSS signal or because the area was completely GNSS denied, I could just switch over to SLAM, and that's going to be a direct replacement. That certainly was not the case. SLAM does require a bit of a different mindset and different planning to data collection. So unlike your drone-based collection, where you have flight planning and GNSS signals, structured GCP placement that are going to be your key factors, remember in SLAM, you want to have those key geometric features that you can return to if you want to get survey grade accuracy. So making sure you understand your site, how you can keep returning to those well-defined geometric features during data collection is going to be crucial. So you want to identify those strong geometric features, which are going to appear multiple times. I do, if you are able to, set it up so that you are starting in a, you have your GNSS data, you're collecting it you start out in an area that is GNSS enabled or GNSS accessible prior to going into the denied or poor area. If you do intend to co-align to GNSS data when processing, so starting in that GNSS enabled area is going to be really critical. Also, want to make sure that you are carefully planning your GCP placement. That's going to, slightly differ from drone surveys. As I mentioned earlier, you don't want those GCPs to be set up in a linear manner. Try and get them more in a, where you have offsets. Kind of a triangle would be perfect, but if you can't achieve something like that, trying to get a non-linear GCP placement is going to be something that's critical for getting survey grade accuracy. Again, not to sound like a broken record, but proper preparation before collection can make or break your survey. SLAM does require manual movement, which means planning your walking path ahead of time. As I said earlier, every site I go to where I'm doing SLAM collection, I do a pre-survey walkthrough where I just have the dock and the rod out, and I'm thinking about how I want to go through, how I want to find those features, if I need to do any painting motions to get underpasses and full coverage for them, and also time on site. So it may be different what you need for your drone-based survey versus your SLAM-based survey. Just because your SLAM data collection might be quicker than a drone-based site doesn't mean that, you know, it doesn't require any less thought. You know, so really taking the time to go in there and make sure that you've thought out how you want to collect data on site. Because ultimately the goal is to be confident that the data you're collecting will allow you to achieve the results that you need. So whether that's SLAM-based LiDAR or any other LiDAR methods, having an understanding of the strengths and limitations of each method is going to help you understand what you need to do to get the best possible data set and achieve your survey goals. So with that, we're going to start wrapping up. Let me see if I can come over. I haven't had questions that have come in. All right, so we've got a question right here. So will it work inside of a large diameter pipe? So 10 feet concrete pipe, the pipe walls will be damp, and it's 20 feet below the ground and 9,000 feet long. So Josh, thanks for that question. What I will say about a large diameter pipe, if you think back to that Kipling underpass, your pipe is likely going to be not have a lot of features. And so that's going to be your main limitation, is especially too, because you're not going to be able to get any GCPs in there. And if you're doing something that's 9,000 feet long, you can't really do loop closure and come back to a feature. So I do think that you would have a pretty significant concern about drift in that area. But I really am interested as to what kind of project you're working on where it's 9,000 feet of pipe and the pipe is 10 feet in diameter. That's pretty impressive. But Josh, if you do want to reach out after this session, you can just email support@rockrobotic.com and we can discuss what you might want to do to try and prepare or get data at a site like that. All right, so from Logan, what are the best practices for mobile mounted SLAM for longer roadways? And you say you're using the R3 Pro V2 and the V2 dock. So best practices for the mobile mount SLAM when you're using roadways. So you've got the GPS data. And so what I would say is that as with anything is making sure that you have high quality and nearby base station data for that you're going to use in the PPK processing. So for whatever base station data that you're collecting, you want to have a 1 second interval for data capture, Rhinex 3 file format, but also you are connected to as many possible satellite constellations and therefore total satellites for the duration of your survey. So if anything is going to reduce your accuracy really quickly, it's not having a good satellite count. And so making sure that you have as many of those satellite constellations and therefore satellites would really be helpful. The other thing I would say, and again, this comes down to planning, is drive your survey area before you collect it with the mobile mount. Because you want to, again, ensure and see what kind of GNSS obstructions or GNSS-denied environments you may be going through. So if you are doing mobile mapping and you're going through a road which has, you know, some multi-story buildings on both sides of it, that could be sort of a GNSS-denied canyon. And in that area, you're going to get poor GNSS signal, and that's going to reduce the accuracy. And we could see some misalignment in data collected at different times at that same point. So again, understanding where you may have areas of poor GNSS connection or total GNSS denied and trying to reduce that. That would be my recommendation for your mobile data. Again, if you want to discuss that one-on-one or get into more detail, Logan, you can send an email to support@rockrobotic.com. If you want to include a KMZ file of the roadway path that you would want to survey with your mobile setup, and we can take a look at it and try and understand what limitations or what things you'd want to consider for that data set. So Gregory, can you register SLAM data to a higher accuracy point cloud, say from an SX12? That is something I am not sure about this time. I don't, so SX12, is that a different unit for SLAM capture, or is that a different processing workflow? I'm not positive, but again, support@rockrobotic.com, maybe with some more context and details, Gregory. I'd be happy to try and answer that after this. And with that, we are on the hour exactly. So again, I want to take a moment to thank everyone for attending, bringing their questions, and frankly, putting up with me for an hour. As I said, it's our customers and users who kind of put Rock in the best position to improve and evolve our product offerings. So please come back and let us know, if you found this helpful, where you think, what other topics you'd really like us to see do for live streams, what questions you'd like answered, and we'll be happy to address them in the future. Again, thank you very much, and I hope you have a great rest of your day.
Thank you for joining us for today's event and being a part of this incredible journey. We here at Rock Robotic hope you're feeling inspired and ready to take the next step. Feel free to reach out to our team for any and all questions. We're here to help you decide what's the best fit and right for you. Together, we will rock on.